Right, it's just 1 minute after 4 p.m. And I'm expecting that we must go up to at least a minimum of 1 minute after 6 p.m. Okay, we're going
Yes.
to be looking at linear algebra today as you know it. But we
Mm-hmm.
shall be focusing obviously on the exam preparation part of it.
Mm-hmm.
We shall be focusing on subspaces, spaces, linear independence, and other aspects that really sort of underpin this module. Let's get started now. I've gathered hundreds of questions and I was thinking of gathering even much more. In which case, then obviously we shall have the opportunity to do as many questions as we possibly can. And
Yes.
so, yeah, we shall practice today. Okay, let's get started with this particular one. Okay, this is the kind of question you can expect to meet. I know that
Mm-hmm.
it's pretty straightforward, but it's very important that one has the understanding on how to do this particular question.
Mm.
Right. I need to confirm, are you able to see the question?
Yes, yes, I
Thank you
can
so
see.
much. Okay, right. So you have that for a given function f, for example, that is of the form that is stated, for a given function that is of the form that is stated,
Mm.
right? F is it's a function from the real numbers to the real numbers. It is defined as obviously a linear map, a linear function. It is a straight line function. The image
Mm-hmm.
of the set S is which one? Okay, obviously I'm sure that this is a very popular question. You might be knowing the
Yeah.
answer by just merely looking at it. But we shall discuss the
Yeah.
methods on how to go about doing this question. And we get started now.
Mm.
Right. So what are the methods that one needs to know about this particular question? And what do we need to also sort of understand about it? It is the fact that the set S, right, the
Mm.
set S, you agree it is obviously containing all real numbers. Okay, X is the real number. It's not even a vector.
Mm.
Such that you have actually x squared minus 9 is greater equal to 0. Okay, I'm just rewriting this at S.
Mm.
Now, this set, you'll agree with me that what we have in this case, you can write it outside the set. It is x squared minus 9 is greater equal to 0. This can be factorized into x minus 3, also into x plus 3, something that is very much known. What are the
Yes.
solutions to this? From the school curriculum, you will understand that this would have a minimum vertex. There are two critical values of this inequality. What are they? They are minus 3, for example, together with plus 3. Okay, right. We ordered them on the x-axis. This quadratic must be greater or equal to 0. When is it greater? It is equal to 0 here. We agree it is greater up. It is equal to 0 here. It's greater upwards. Okay. That said, it means the solutions to these can be written below that. And we can say x is less or equal to minus 3 because if we were to go greater above the x-axis, above 0, so we actually are migrating towards minus 3, or
Mm-hmm.
obviously we're saying this quadratic is greater than 0, so we are above there, which means x is bigger or equal to 3. Now, what
Yes.
is the meaning of these? These are the two solutions. However, this linear function up there can be seen
Mm.
as the following. What is f at minus 3, for example? Okay, if
It's
f
what?
of x, let's start from there. Right, f of x is x plus 4. What is f of minus 3? So that's going to be minus 3 plus 4.
Mm.
Obviously, also here, Look, the function f was given there. It was given as f of x equals what? X plus 4. Okay, this must not surprise you, this question tomorrow. What is then f at 3? It is actually 3 plus 4. And what is 3 plus 4? 7. Okay, minus 3 plus 4 is plus 1. Okay, these are the kinds of questions you'll see. First question tomorrow. It can just change some numbers here and there. It may just be the same one. Okay, right. So now, these are the two things. So we are effectively saying, what is the image of the set? This image of the set as under the function f, because the given function is defined by that. So it means there are two things here, Mahote. From -3, at -3, the image of the function is 1. But x starts from -3 and progresses to what? Progresses towards minus infinity. So, and that means the function, the image of the set S will actually therefore be as follows. Okay, the minute this one goes to minus infinity, so it means also the image will go to minus infinity, but it's gonna start from at -3 where the image is +1. Okay, so you have these parts on the left and the part on the right. So that is all. Okay, now we also have the part on the right. From 3, this parabola goes up from 3. At 3, it is what? F at 3 is 7.
7.
And then this parabola like proceeds and progresses to infinity. Okay, towards the right. All right, so that will be the image of the actual function. And so that will be the answer. So the question is obviously, which one is this? Because they're saying the image of the set is this. So you need to look at which one is like that. So the first one says none of the above. The second one says 2 and 9, which is not between 5 and 10 inclusive, which is not minus infinity to 10, union 12 to infinity, which is not minus 5 to 12. They have nothing to do with this. So obviously the correct answer would be none of the above options, or none of the given options. Oh, yeah, none of the given options there. Okay, just note that. So yeah, we are recording this discussion, so you'll have the chance to go through these again.
Okay.
Right, so we proceed now. I'm sure that this is pretty straightforward, and there are more questions you shall see. Right, the next question is about a very popular trend, and it's the kind of stuff you can expect to meet tomorrow. Right, so what this kind of question? You must be able to find the eigenvalues and the eigenvectors. So I'm going to look at a lot of questions on these, but this one I decided to bring because it's very interesting, and we need to indulge and have fun here. Let's get started with this one. Okay, given this map, it's a map. You need to find all its eigenvalues and eigenvectors. Okay, so you need to know how to go about doing these. And now, what methods do we employ here? So we start as follows. So we look at actually the map P of xy. That is the map. What is this map?
Is it 25 marks, Vel?
Please come again.
Is it 25 marks, or that's the total mark?
Oh, is it 25 marks?
Yeah.
It is 25 marks.
Oh, okay.
Yeah. Okay, so yeah, because it's a lot. Okay, there's a bit more work. Okay, I've taken it from the material, but yeah, I did 25 marks. But it's a good one. Okay, so, but this is how we start. Okay, so in other words, we can start and say to actually find First, we'll find the eigenvalues and the eigenvectors. So to find the eigenvalues, how do we go about finding the eigenvalues? The eigenvalues of t, how do we
Mm-hmm.
go about it? So which is lambda into xy. Right, so we find the lambda into xy. So in other words, we're interested in the kind of relation that
Yes.
actually satisfies these inequality. And what is then at this point, what is actually txy? Okay, t of x and y is
X
x
minus Y.
minus y
Okay.
together with 3x. Okay, which is lambda into xy. So, okay, it is this actually. T of xy is x minus y into 3x. 3x. Right, so what is the answer to this? Okay, so obviously at this point you can proceed as follows. X minus y, 3x is equal to lambda x. So these are exam type questions. So these are the kinds of questions you'll expect to meet, and that is what I was putting together. So you compare the components. So the first component equals the first component.
Mm-hmm.
Simultaneously, the second component equals the second component, which is lambda y. Okay, so this is what we then get. So what is the meaning of all these and what do we then achieve from these? So we need to actually therefore solve simultaneously out of this. So
Yes.
how do we therefore solve simultaneously here? So these become simultaneous equations, right? If these are simultaneous equations, how do we therefore go about solving this? Because this tells us that we have 3x equals this.
Yes.
So if 3x equals this, we can make, for example, y the subject or x the subject, so that we
Mm-hmm.
have lambda y out of 3, for example. Okay, so you can call that an equation 1. Okay, let's call it equation 1 for argument's sake. And then now you have another equation, this one here, which is x minus y is equal to lambda x, and call this equation 2. Right. So you can say put 1 into 2. Right, so if you put actually equation 1 into equation 2, what do we get?
Okay.
All right, we put it into that. So we have all that. So what we achieve at this point is that wherever there is x, we shall put this. So it is lambda y over 3 minus y is lambda. X is lambda y out of 3, which is lambda y. Right, so this is actually lambda y out of 3 minus y is equal to lambda squared y out of 3.
Yes.
Right, so we achieve exactly this.
Yes.
Okay, see. I've made a lot of space available within in the question. So you have lambda y out of 3. So you can write here lambda y out of 3 minus y equal to lambda squared y out of 3. Okay,
Yes.
so you can write this one as lambda y out of 3 minus y minus lambda. So these are typical exam questions. They're not just the stories, this. Right, so these are the kinds of things you'll see tomorrow. So you have lambda out of 3 minus 1 minus lambda squared out of 3. This equals what? 0. And what do we get at this point? Right. So this actually would mean that ordinarily we actually do not accept that because if ever we would allow y to be 0, then x is going to be 0.
Yes.
And that, well, I mean, if y is 0, okay, if we say y, because we have an equation here, so ideally we would prohibit y from being 0. And because if ever it happens that y is 0, then x is 0. And then we have a 0 vector. But eigenvectors are never 0 vectors. So this means that in this equation, when we multiply this and that, we're getting 0. Y is not 0. In lambda out of 3, minus 1 minus like lambda squared out of 3 must be 0. Okay, multiply through by 3, okay, which is lambda minus 3 minus lambda squared equals 0. Divide through by negative 1, which is lambda squared, minus lambda plus 3 equals 0. Okay, I've divided through by or multiplied each term by negative 1, and this is what we achieve. Okay, when we get to this point, we are interested in seeing what we get as the actual values of lambda. What are the values of lambda at this point? Right, so we look at these obviously and begin thinking, are there factors of this expression or not? Okay, and obviously you can see that there are complex roots out of these. There are complex roots out of this. So lambda, for instance, is going to be minus b plus or minus the square root of b squared minus 4ac out of twice a. Okay, so we have this. And therefore lambda equals, okay, so yeah, we have this, so it's minus into minus 1. Okay, and then we have plus or minus the square root of the b squared, which is minus 1 squared. Minus 4, the a is 1, and the c is 3. All these is divided by twice a, which is 1 plus or minus. 1 minus 12 divided by 2. 1 plus or minus. Okay, so what does this give us in the end? Right, so it gives us the square root of minus 11 divided by 2. 1 plus or minus, the square root of this is actually I times the square root of 11 divided by 2. Okay, so these are the values of lambda. And therefore we have that lambda is 1 plus I, the square root of 11 divided by 2. Or we have that lambda is 1 minus I into the square root of 11 divided by 2. So these actually become the eigenvalues. So yeah, these are the eigenvalues of t. Right, these are the eigenvalues of t. Okay, if these actually become the eigenvalues of t, what then are the eigenvectors of t? Right, so let's then proceed to find the eigenvectors of t. Right, so Obviously, there are a couple of ways we can use to find the eigenvectors of T.
Mm.
Right. So to find the eigenvectors of T, we proceed as follows. Right. For the eigenvectors. Right. For the eigenvectors. Right, of T, we proceed as follows. Right, we do a case-by-case analysis. So for lambda 1, for argument's sake, which is one of them, like the one with the plus. So 1 plus,
Mm.
1 plus I, the square root of 11 out of 2. We perform a substitution. Right, so we perform a substitution, and if we perform a substitution into one of the vectors. All right, so this is how we go about doing it. Right, you need to remember that we actually have the eigenvectors, and the eigenvectors are of the form lambda into that. Right, so if it's lambda into xy, is actually what we called t of x and y. So t of x and y is lambda into that expression. So thus we can say if we have lambda into xy, for argument's sake, it is therefore the same as lambda x, lambda y. Okay, so you multiply straight away into the vector. Right, so now, and what does this mean, for example? Well, it would mean a couple of things, but it would mean therefore at this point, we would have this vector, which is 1 plus I, the square root of 11 divided by 2 into xy. And what is all this? Right, so you allow this vector to multiply straight into, or this complex number to multiply straight into the vector. Right, so this is going to become 1 plus I, the square root of 11 out of 2. You multiply first x, and then you have 1 plus I, the square root of 11 out of 2, and this multiplies y. Just this way. Okay. Right, so this is what we get. But a couple of things we need to remember from where we started. What should we remember? We need to remember that obviously what we're having is that x is equal to, so x can be written in terms of y. So x is equal to lambda y over 3. We use that.
Yeah.
So we remember that x is lambda y out of what? Out of 3. So which means therefore, wherever x is, you can put lambda y out of 3. All right. And therefore, this means that we can write the following. So at this point here, you have lambda y out of 3. And therefore, this would mean x is lambda. What is lambda? Okay, so lambda is, for example, 1 plus I, the square root of 11 out of 3.
Mm.
Okay, that is lambda out of 2. Okay, that is lambda out of 2, right? So, but obviously this is the lambda, and then you have y out of 3. Right. This is what we get. So in other words, we can write x that way. If you can write x that way, we can take that and substitute in the place of x, for argument's sake. So we can take that and say, and remove this and come here. Right, wherever there is x, right, we have lambda x. Right, so in other words, this is lambda x, that is that. And also you can see that, alternatively, you can actually see that this one here is lambda y. Lambda y, according to this, is 3x. Okay. So which means that here you are seeing lambda y, but wherever you're seeing lambda y, you can write it as what? So all these are equivalent steps anyway. So you have these x. Okay, this is lambda y, this component, but lambda y is actually 3x. And that gives us an eigenvector. So what is the eigenvector? You can factor out x, or you can factor out x over 2. Okay, just to avoid fractions, you can factor out x over 2. And this is 1 plus I, the square root of 11 x here. And therefore, if factor out x over 2, what will this one be? It's going to become just 6. Right, so that gives us 1 plus I, the square root of 11 out of 2. Right, so this is one of the, so in other words, you can always say.
So why are we still multiplying by x where else we factored x out?
This x, yeah, so obviously this x actually is out. Thanks for realizing that this x is, you can just totally remove it because it has been figured out. So yeah, you're on point. So yeah, it's fine now. So I'm happy that obviously you're following. So you note therefore that you have one of the eigenvectors. So in other words, one of the eigenvectors of the eigenvectors, right, is of the form okay, we say normally it's of the form x over 2 into 1 plus I, the square root of 11, then 6. Or you can say the eigenvector is, or an eigenvector, because the equivalent is eigenvectors. There are many of them, right? Of the form that. So you have eigenvector. Right, you can take this one, for example. Okay, so we can take the eigenvector 1 plus I, the square root of 11, and 6. For the 1 plus I, the square root of 11 out of 2. But yeah, there are many others. Like at this point, somebody would have factored only x. You factor only x, you'd have your eigenvector with a 2 in the denominator here, which will also be correct, and a 3 there. So yeah, these are equivalent vectors. Right, so looking at these very, very carefully, what is the meaning of this? But yeah, I'm going to actually also mention for the other eigenvector, for example, the other eigenvector, what is the other eigenvector has other eigenvalue has a minus, here. So they differ just by a sign. So you would say for lambda 2, so these vectors will look very similar to each other. Okay, so you take this one, which is 1 minus I, the square root of 11 out of 2. Right, so you proceed with the kinds of steps, yeah? But now where will the difference become? Okay, so you would have that at this point, so you would still have a situation where there is lambda y, when you multiply, you'd have a 3x. But now this vector is going to be a different vector. So you're going to have 1 minus at this point. Okay, you don't need to write all the steps like we've done for the rest of this other one, because these are just complex conjugates. So you have that, right? And then you'd have x, like so. And then obviously now you have a lambda y. Lambda y is 3 times x. So what is the eigenvector? Right, so obviously you have form of the eigenvector. What is the form of the eigenvector? Right, so the form of the eigenvector, it's going to become, when you pull out something of your choice, you can pull out only x, but normally we pull out the fractions, the denominator sort of expressions. Right, so we can decide to pull out at this point x, we must pull out x, but we can also pull out the division by 2. And if we do that, we're going to have 1 minus I. Okay, it's popular to do it this way in mathematics, and then you can put a 6 here. Okay, so you can really see that these are, so in other words, therefore, we have the eigenvector. Right, what is the eigenvector? You can write it as 1 minus I, the square root of that 6. So we have found two things. We have found the eigenvalues, and we've also found the what? The eigenvectors. Okay, so yeah, we most certainly are on point. Just note that precisely. Note it exactly. Any questions? No questions. Okay, obviously, the most important thing is understanding just the method and what's happening, and how to do this. Because with any other question, you can like use the same method the whole time, all the time, to like solve the problems. So yeah, I have more questions. The next ones are plenty, and I shall be passing through them. The next set of questions, obviously, they follow the exam nature, so you really should not be surprised. Okay, there are questions like this. Consider f equals this expression where x is a real number. Then which of the following ones is true? F is not a function, right? F is a surjective function. F is an injective function. None of the given answers. So which one is true about this case here? Okay, so you need to think about this. And you need to think carefully. Right, so you need to think very carefully. Which one? Is it a function? Is it surjective? Is it, okay, so we discussed it. First and foremost, you will write the function f as follows. I mean, it is given. It contains x in the first component, then it has sine x, then it has minus I cosine x, and it has x an element of r. Right, consider f, then which of the following ones is true? So we agree that at this point, f is actually a function from the real numbers, because x is a real number. It's actually a function, a map from the real numbers to the complexes, because now you have the I here, and I is a complex number, it's an imaginary number. So this one here is a function. Right, so it is a function being of the range Okay, what is the range associated with this function? The range associated with this function is, it contains um, certain complex numbers that have certain properties. Like if you take this complex number, this is a complex number, and you square these, what do we get out of these here? Okay, so you can view these as f as containing some complex numbers z of modulus 1. Okay, I'm going to elaborate on the modulus 1, but f is not surjective. Why? Okay, we'll discuss this. It's not surjective. Okay, if you don't want to use this, the word surjective is not an onto function. Right, and it's not an onto function since a couple of things are important. Like your 2 minus 3i together with your 3 minus 3i. Okay, belong to the range of f. Right, they belong to the range of f. Right, so in other words, it's not necessarily a surjective function. Because the function f itself now produces this. When it produces this, it means that you really can have a couple of entities, like this is the x and this is the image. If you let z to become sine x minus I cosine x, then you can be able to find the length of this. Okay, the length of this in mathematics is the modulus, which is the square of the real part. Then we have the imaginary part, which is minus cosine x, and then you square this part here. Now, what is the sine squared? So you have sine squared x plus cosine squared x. What is sine squared x plus cosine squared x? Okay, that one is 1 square root 1. So, and hence that is why we have that this is the property. So this, what kind of a description is this? So this describes a unit circle. It describes what you call a unit circle. A circle of radius 1 is defined like this in complex number terms. Right, so you have essentially that. Right. So there are a couple of things, for instance, but also we proceed to say f is not injective. I'm going to elaborate more on this here. But f is not injective. Right, so f is not injective. Why is f not injective? Right, it's not injective since f of 0. Okay, right, because you can see this here. this is the same as saying f of this x is the same as sine x minus I cosine x. Okay, it's kind of question with me. But when x is 0, you have sine 0, which is 0, and then you have cosine 0, which is 1.
Mm.
So this thing is like minus I, but also f of 2 pi. So it's not one-to-one this, because you have a situation where there is 0 and there is 2 pi. Both of them, they become minus I. So the function is therefore not injective. Okay, it's not injective. Right, so which one therefore becomes the correct option? Or it is none of the given answers. It is none of the given answers.
So if it's injective, it's
Yeah, if it's injective, then it is one-to-one.
oh, if it's
Okay, yeah, if
subjective,
it's one-to-one, then it goes this way. Okay, because you see, the thing is that we actually have possible difference, because they're saying here, consider f, then which of the following ones is true? So we're just looking for a true statement here. So we need to think of all these to say, is it subjective? Is it injective? Is it all those things? And it is certainly none of them. That is why we have none of those. Because in essence, what we are having here is the usual suspect. Is it a function? It is not a function. Okay. Perhaps obviously the kind of thing that we discuss, how is this not a function? Okay. So you have x and y, and then this one is the real part of z, and this one is normally called y, but you can call it the imaginary part of z. And so if this is the case, what we're having here is we are having, we looked at this case. So if you look at a unit circle like this, then that is the origin. By the vertical line test, okay, a function must, because the first says it's not a function. Right. So is it necessarily a function? Right. So those are the kinds of things you need to look. All right. So you need to look at the most correct statement to say, is it a function or not? Right. And obviously you can see that it actually, according to this here, because if you consider f of x to be this, and you take the modulus says you square x, you square y, what we are getting is a unit circle. And a unit circle, therefore, has its own range. Right. And what is the range of this? Is just all those numbers of length 1. Though all those complex numbers of modulus 1. And therefore, you could see that if you take the length of this, or the modulus of this, it's 1. And now looking at the unit circle, the vertical line, a vertical line that cuts through these does not cut it only once. It cuts it in multiple places. It cuts it twice. Any vertical line will potentially cut it twice. And because of the many vertical lines like that can go through between two extreme points, you actually realize that it fails in many ways to be one-to-one. It fails to be an onto map. And therefore, it is safe to say the most correct option here would have to be none of the given options is necessarily true. Because As I indicated, that the one-to-oneness would mean here it doesn't go to the same image. It goes to, from 0, it would go to its own image, and from 2 pi, it would go to its own image. That kind of thing. Okay, so I'm sure that we're going to have a detailed discussion on this. All right. So we continue. Okay, the cube roots. Okay, you'll actually always expect a question like this. In terms of the cube root of this is which one? Okay, these questions are funny sometimes. Right, so to find the cube root, you just have to let z to be 2 plus I. Then you have the modulus. 2 squared plus 1 squared. Square root of 5. Okay, which is we're seeing that one. The real part of z, imaginary z. Okay. You measure this. Okay, and whatever that becomes. So which one is this and what is the actual, okay, because this complex number here is having x is 2, and you can call this I here, call this theta. So you'd have the tangent of theta, which is y over x. What is y?
Y
Is 1 out of 2.
Yes.
Okay. So the angle theta obviously will be associated with the arctan of this.
Oh.
Okay, so you can just use the calculator for that. In terms of the arctan, you'd realize therefore that the arctan of that would be the arctan of 1/2. Okay, so it's a decimal, which is none of that. Okay, so let's just do it. Okay, I'm just doing the arctan now. Right, so the arctan of 1 out of 2.
26.57.
Right, so 26, right?
Yeah.
26,57 degrees, or in terms of radians is 0,4636 radians. Okay, we use radians here. You'd have to compare with any of these and say like, okay, when I get to those. What will the cube roots be? Well, the complex number can be written as, okay, this complex number. Okay, so what is this complex number? So this complex number, which is 2 plus I, yeah, I, is r into cosine theta plus what? Plus I sine theta. What is r? Okay, we found r to be the square root of 5. It is here. Cosine theta. Theta is actually 26. Okay, you can use the radians. So obviously it's a decimal, so the best would be to use the radians. But you can use degrees as well. Okay, the radians would be 0,4636. Zero comma 4636. So you need to find the cube root. So you have this one. So which is 0,4636. You add to it 2 pi k, and now you want to divide by what? By 3. We need to compare with these answers, and see if any of these works out to that.
Mm.
Okay, so this is because this will be the answer, and then you compare. Right, so we're going to compare together. So you have I, the sine of 0, 0.4636 plus 2 pi k divided by 3. Okay, so, but it is true for, okay. This question uses n, but yeah, k 0, 1, 2. Because the cube root, then there are 3 values of k.
Yes.
Okay, so yeah, we need to compare with any of this. And see, okay, you can see the 2 pi, the 2n pi over 3.
Mm.
Okay, like if you look at pi out of 12, okay, but also one giveaway would be this part here. This is square root of 5, but this is raised to 1/3.
Mm.
So it can't be this, it can't be that. This is possible because the square root of 5 raised to 1/3 would be, which is 5 to, okay, sorry. This is 1/3 and this is the square root. Square root and 1/3. So this is like 1/6. If it is 1/6, um,
Oh, yes. Yes.
yes. So you would then realize, therefore, that you have this here, and if you have this here, it would be this. It could be this. But let's check the inside. So you'll have to check this part. Okay. So to check this part, now you can see this part, the 2 pi k over 3. Yeah. But what about this one? So you check 7 pi out of 12 and see what this is the same as. Okay, I'm going to use a calculator. So that would be 7 pi out of 12, which is 1,83.
Yes.
259, obviously approximately. But the question is, if you have 0,46 you divide it by 3, can it be 1 comma something? It can't be, because 3 is even bigger than the numerator.
Mm.
So these were expected even to be less, 0 point something. And therefore, in view of that, is none of the given options. It is
None.
none of the given options. Okay. It is none of the given options. So we continue. Right. Suppose X is this, is in C such that this is the case. Then X is which one? Okay, this one is easy. Okay, we can just deal with this one. So here we just have 1 plus 2i minus 5 minus 4i plus x is 3 minus I. So let's solve for x. Okay, before you solve for x, let's just add this. 1 minus 5 is what?
You too.
Is minus 4. Okay, we have 2i minus 4i, which is minus 2i. And then this is 3 minus I. Um, What is x? You move this across. 3 plus 4. It's 7. Minus I plus 2i, which is 7 plus I. So, yeah. Right, there's none of those, obviously.
Most questions are none.
Please come again.
I'm saying most questions are none of the
Yes,
above.
I none of those. I agree. Yeah, but yeah. So we're just doing exam practice because you expect to see these. Okay, there's another question I'm gonna do. Yeah, I think I did not include it here, but we're gonna talk about it. Okay, next. This one also. Subspaces. What is a subspace and what's not? Okay, so let's look at these. Is it a subspace or not? These here. Okay.
As
We note that this let S be the subset of R cubed. We should define this. Then you have those. Okay. S is a subspace of R cubed. Yes, it satisfies um, the following. The following conditions. The following conditions of a subspace. It satisfies the following conditions of a subspace. Following conditions of a subspace. Okay, here we don't even need to do a lot because anything in mathematics that is of the form ax plus by plus cz equals 0. It's a plane. It's a plane through the origin. How do we know it's through the origin? The origin is 0, 0, 0. Okay, if you put x 0, y 0, and z 0, everything is going to be 0. So it's a subspace of R cubed as it satisfies the following conditions of a subspace. What is the first condition? So you have 0, 0, 0 is an element of S. Okay, the origin is an element of S because if you put x 0, y 0, the left and the right are equal here. So
yes.
this one is a member, this vector, the 0 vector is is an element of the set S. But also point number 2 is the sum of two vectors. Closed under addition of two vectors or more for any S, yeah, you can call S1, S2 in the set S implies S1 plus S2 is an element of S. Well, the thing is that it is a plane through the origin. So planes through the origin have no problem because if you take one plane through the origin, you add to another plane through the origin, you will get a plane through the origin. Why? Well, I can have this plane through the origin like that one, and then I have another one, right? If I have another one, I have the blue plane. If I have the blue plane, I have a1x plus b1y plus c1z equals 0. Okay, if I add the a1 and a, b1 and then c1, okay, if I add them up, I'll get a plane through the origin. So it's a consequence. The sum of two planes to the origin is also a member of. It's also a plane through the origin and therefore a member of S. Right, next, so last but not least, the third condition is scalar multiplication. This is vector addition. Then the third one is scalar multiplication. For example, for any scalar, A in the field, and any S implies that AS is an element of S.
Mm.
If you take a plane through the origin and you multiply it by a number, a field element is the field, like the set of real numbers is the field.
Mm.
And the set of complex numbers is also a field. So if you take a plane through the origin and multiply it by a number, then it's not gonna change from being a plane through the origin, just that it's gonna be multiplied by a number. But it's gonna still be a plane through the origin, and therefore multiplying by a number does not change the fact that it's a plane through the origin and therefore a subspace. And as therefore conclude that S is a subspace of R3 as it satisfies the following three conditions of the subspace. The origin satisfies the plane equation, and the sum of two planes produce a plane, and the scalar multiplication as well, if you multiply these by a field element, also satisfies that, and therefore we're good.
So it's a
Okay.
subspace.
So obviously now in question 4, we ask what is the question? So it is clearly a subspace of R3. It's clearly a
So
subspace.
Stan, you have to prove all the conditions, or if you prove one, it's fine.
That's a good question. Obviously, you need to prove all the three, the 0, 0, the S1 plus S2, and the A times S. You see, like tomorrow, there are going to be those questions that are long, you know? So
Yes.
those questions that are long, where you need to just submit some PDF.
Yes.
There are those MCQs, but there are those long ones. So with the long
Yes.
ones, very likely this will be the kinds of questions, you know, like prove is a subspace and you need to prove like the three conditions, you know?
Yes.
So
Okay.
it's something that you can actually surely expect. All right. So S is a subspace here. Obviously, it's an obvious one because all planes through the origin. Something that is not cannot be a subspace is like if you take a plane like this, x, y is equal to 3z. Like you're writing this one, x plus y equals 3z minus 5.
Mm.
This one is not going to be a subspace because it doesn't pass through the origin. Because if you put x,
Yes.
y, and z as 0, you'd have that 0 is equal to minus 5, which is not true.
Yes.
And that would mean, therefore, this plane does not pass through the origin. It's a plane passing through some other place in the three-dimensional space, making this plane not to be a what? Not to be a
Subspace.
subspace.
Mm.
Okay, yeah. Next. Okay, linear independent vectors. Okay, there's a question like this tomorrow. So please, right, the vectors like these are linearly independent, do not span, linearly dependent, none of the given answers. So obviously this one you need to just check very quickly, and it's an obvious thing. So so you actually let x, y, z be elements of R, so that you'd have x into 1 minus 1, then 2, y. Okay, you multiply the first one, the second one, so which means that we have x plus y plus 7z equals 0 minus x plus 0y 3z equals 0, then you have 2x plus y plus like 0, z equals 0. At this point, you have this 1, 0, 1. You have 7, 3, 0. And then you have this. Okay, we just need to deal with this augmented matrix.
Mhm.
Okay. This augmented matrix would be, okay, we already have a leading one. Row 2 plus row 1. So you have 117. So you have this. So row 1 minus row 2. 1 minus 1, 0.
Mhm.
Okay. All right. So we have this. All right. So you have this. Okay. So that's row 1 minus row 2.
Mhm.
Minus 3, 0, 0. Row 3 plus row 2. 0, 0, minus 4. Minus 1 over 4, row 3. Okay, so which is row 1, goodness me, 3, row 3, 0. Row, now I want to produce a 0 here. So I'm going to use row
Yeah.
2 minus 10, row 3. 0, 1, 0, 0, 0, 0, 1. Okay, obviously we started with the x, y, and z. So the first row means x is 0. The second one says y is 0. And the third one means z is what? Is 0 as well. So in that means they're linearly independent.
So say I saw somewhere
Yes?
where I think the textbook
Uh-huh.
they say if you add vector 1 and 2 and then it adds up to vector 3, then it's linear dependent.
Yeah,
Or if you do the
then to
determinant,
linearly dependent.
yes, but
Yeah,
it's not. Vector 1 plus vector 2 is not equals to vector 3. So it's
yeah,
out.
definitely. Obviously, I mean, that sometimes is possible, but it's very tricky to always see.
If it
Because,
is,
I mean, if you add these two and you get these, they would be linearly dependent.
yes,
Or you add any two to get another vector, maybe you add the first and the last to get the middle vector.
yes,
So they're linearly dependent. That is true.
yes.
So
So even
yeah,
doing the determinant of the vectors,
yeah, if you
if
find the determinant of the vectors,
if
like you see the way we've written them, the
yes,
way we multiplied with the x, y, and z.
Yes.
And then now, how are they sitting, these vectors? So this vector now is a column.
Yes.
This one is a column vector. And this
Mm-hmm.
one, the 730 is now 730, but it's a column. The
Yes.
101 has become a column. So you can just, another way is to just find the determinant of this matrix here. Because
Yes.
the determinant of the coefficient matrix. If the determinant is 0, it means that the vectors are dependent on each other. There's linear
Yes.
dependence. Because if the
All right.
determinant is 0, it means that the vectors are just like the same.
Mm-hmm.
So that when you minus 1 from the other, the result is 0. Because dependence means that one is a multiple of the other, to the extent that just like one multiplying one vector by a number 2, you know,
Yes.
and that
Yes.
still produces linear dependence.
Okay.
All right, we move to the next question. So the answer here is linearly independent. But the easiest
Oh,
way, the most accurate, is to calculate, because here, this is the definite proof. If vectors,
okay. So what?
a set of vectors passes this test, yeah, it
Mm-hmm.
is the correct set of vectors.
All right.
Yeah,
So what does it mean when it says it's a span?
yeah. So obviously the span,
Yes.
right? So sometimes we speak about the span. Okay, we can find the span of this. So
Yes.
you will find the span of a set of vectors like this one. Okay, the span of this one. Yes, span means linear combinations. So if they ask you to find the span of this,
Mm.
what is the span of this? It means that you can take x and multiply the first one, y multiply the second one. It just means linear combinations like this.
Oh,
Z times the third one.
okay.
And then you have x, y, and z. You get the point? Yes,
Yes.
you can take these to be like real.
I can't see at the corner there. There's a
Yeah, I
picture of
see I'm
you.
writing too high. Okay, I'm trying to squeeze it. Yeah, let me just bring it down here. I'm just trying to squeeze it, but it's not. I'm just elaborating on the span. Okay, the span of this would be what? The span of this, it
Mm.
would be x into the first one plus y into the second vector plus z into this one,
Yes.
where the x, the y, and the z ideally, I mean, if we was doing things over the real numbers. So this is a span, this.
Mm.
But you write the span like I wrote in blue, and then it is equal to this in green.
Yes.
So what is the span? Well, the span of a set of vectors is a set of all linear combinations of those vectors in this manner, you know?
Yes.
All right,
All right.
next one. Let's continue now to the next question. What is the next question? Okay. Now there's another question, this one. Let S be the subspace of R5, defined by that one. So now, what do we get? Then the basis of S is given by what? Is given by this. Okay, we're asking, obviously, specific questions in terms of this. Then the basis of S is what? Okay, let's continue. Let's solve this one, question 6. Right, to solve this one here, we're interested in the basis of S.
Mm.
Okay, on this node, on this question, you can just find the determinant of this. Determinant of 1, 1, 7, then minus 1, 0, 3, then
Mm.
2, 1, 0. Okay, you can have the matrix, you can write a matrix A like
Mm.
this. And then, okay, the determinant of this can be found, but we found it to be minus 4. And then, which is not 0. Because it's not 0, it means they're
Yes.
linearly what? Independent.
Independent. Yes.
Yeah. I mean, that's another way of doing this question, just commenting. Okay, if you look at
Yes.
question 6 now, what is the basis of this? Okay, so to deal with this one now, you can just do the following thing. Right, so you can take the set S like that. Okay. Okay, you take the vector, this one, that is in S, because you want to find a basis, the basis of S. So you take a vector and then play around with that vector. How so? Okay, you play around with that vector in the following manner. So you consider, for example, x1. What is x1? Is this one. But
Mm.
x1 is also
Equal
this
to.
here.
Yes.
So in the end, what is the basis here? Okay, so you can call x1 to be t. Let x1 to be t where t is a real number. Okay, so you can write it like that. Okay, you continue.
Yes.
Okay, yeah. Okay, x1 is t, and then you continue with the next one. Um, okay, that would mean that x4 is going to be minus x1, so it's minus t. Obviously, t is in R. Okay, we are dealing with this part now. Okay, but also if you let x2 to be S, x3, what is x3?
X1 minus 3.
Is x1 minus 3x2
Mm-hmm.
from this.
Yes.
And then x1 is t minus 3s, for argument's sake. Okay, so which means you have x1, x2, x3, x4. Which is x2 is S. X3 is t minus 3s. X4 is minus t.
Mm.
Hey, And then you get this. Right. So, which means that 0t 0s, okay, minus 3s, which is 1, 0, 1 minus 1. Minus 3, 0. Okay, these are linearly independent. As the vectors 1, 0, 1, minus 1. Are linearly independent. You can check like we did before using the matrix reduction, but it's not necessary, it's obvious. Are linearly independent. And span. Span the set S. How do they span the set S? Because of the linear combination. Hence the vectors. Hence the vectors that and that. Hence the vectors form a basis. They form a basis. All right, so they form a basis. Right, hence these vectors form a basis of the set S. Yes. They form a basis of the set S. They form a basis of the set what? S. Okay, obviously there are just too many ways to think of this question, and I was obviously looking at it in many other ways. And you surely can actually be in a position to find the actual answer to it. And I'd be interested in looking at other methods on the next page, just one other method as well to sort of simplify these question. Yeah, but there are just too many ways to do this particular question. For example, one can look at these as x1 equals 3x2, x1, okay, x1 equals 3x2. Can I just mention this? X1 equals
Yes.
3x2 plus x3. Right, and then you look at the other one, which is x1 plus x4 equals 0. Which means so it's 1 minus 3 So okay, if you have this, okay, you can write this thing as a matrix, this,
Yeah.
which is x1 is 3, so you can write minus 3 minus x3. So when you get to this point, you can reduce these things. So minus into that, yeah, 0. And then here you have 3. Okay, because you have a leading one, this one, right? You can want whatever 0 here. And then now you say this one minus row 1, row 2 minus row 1. That's what I mean here. Right, so here I mean row 2 minus row 1. So you get to the point where you're saying row 2 minus row 1. Right, so row 2 minus that, so it's going to be 0 here. Row 2 minus that, 3. Row 2 minus that, 1. Row 2 minus that, 1. Row 2 minus that, 0. Okay, so row 1 plus row 2, which is 1. So you add now 0, 0, 1. Then try to get a form like this. Okay, now if you look at the leading entries here, you can realize therefore that these entries themselves, they are sort of what? This matrix now is actually a matrix in reduced zero echelon form, because below this one is zeros and it's zeros there above this leading entry. Okay,
Yes.
now there's no way you can perform further reduction here.
Yeah.
And that means, therefore, at this point, you can just be able to see that x1, this one means x1 plus x4, x1 plus x4, because this is x1 column, x2, x3, x4. x1 plus x4 is 0, 3x2 plus x4 is 0. All right, so you can write x1 equals this, and you can also write x2, for example, or you can write x3. x3 to be minus 3x2 minus x4. Then you take the vector x1, x2, x3, x4. Okay, so this is x4. Then you have x2. Then you have x3, which is minus 3x2 minus x4. Then you can keep x4. Then what you get now, if you keep x4, doesn't matter. Okay, keep the x4s together, then 0 minus x4, x4, which is minus 3x2. Okay, these are x2s now. There's an x2 there, minus 3x2, and there's a 0. Which is minus 1, 0, minus 1, 1. Okay, let's do this one here. If you have, you sort of remove this, which is exactly x2 into 0, 1 minus 3, 0, like that. Okay, so what is actually the meaning of these here? What is the meaning of these here? Right. Um, and how is this different from that? We have 1, 0, 1,
Mm.
minus 1. 1, 0, 1, minus 1. Okay, they differ by sign. So I'm gonna copy the actual basis we got from here. If you get a basis we
Mm.
got, what is it? 1, 0, 1, minus 1. I'm gonna write it in red. We got 1, 0, 1, minus 1. 1, 0, 1, minus 1. And then 0, 1, minus 3, 0. 0, 1, minus 3, what? 0. Okay, and then this one now that we got here, what is it? The one that we got now, let me write it in blue. So this one is minus 1, 0, minus 1, 1. And then 0, 1, minus 3, 0. How are these two sets different? Okay. Obviously, you can see that this vectors is like you just multiply this vector by negative to get this.
Mm-hmm.
So I'm just mentioning this because it's one way to do the question, either this way or like this.
Yes.
I mentioned that because I saw that you had x1, x1.
Yes.
So in the x1, x1, you could be could actually be used to perform some reduction so that we have a single 1x1, so that you don't get confused in terms of which one to substitute in the place of x1 in this vector here. Because you must substitute into this vector, but you have x1 equals this and x1 is going to be minus 4. And that
Mm.
creates a dilemma. Right, so either you can use this method or the other one. Yeah, I'm just mentioning in passing. Okay, let's look at this kind of question. It's very important as well. So now it's important that you're able to deal with these kinds of questions. Like this one. Suppose this is the case. Okay, A and B are real numbers. Define T from R3 to R2 by this. So R3, 1, 2, 3 to R2. Then T is linear if. Then T is linear if. Okay, right. The linearity part, what does linear mean? Linear means that P of a vector u plus vector v is P of u plus v. P of alpha u is alpha tu. So this means P is linear. All right. So at this point, always, because it's like the planes, these things, okay? At this point, because now you're just adding these things. And I said that these scalars need to be 0. So for linearity, um, right, for linearity, For linearity, these scalars must all be zero. So B must be zero, but A must be zero, so that we do not have the A and B here.
Mm.
Okay.
Mm.
So for linearity, A equals B equals zero. Then T is linear if what? So the answer would have to be 4 here, none of the above,
Yes.
because A and B must both be zero. Here is 1 and 0, 0 and 1, both minus 1. So um, these things follow the same notion I mentioned of the plane earlier, where we
Mm.
require that these scalars become what? Become zero.
Yes.
So because now they're not zero, well, they have to be zero. They've just been put here as placeholders, but we require that they're zero. Because if they're zero, then we have what is required. Okay, we have what is required. So that is what we get. Okay, so you note that then you note that. Okay, so we proceed. We proceed. We proceed. Um, Let me just. All right, so we continue now to the next one.
Mm.
Right, so this one is none of the above. But let's move to the next question now. Fine, thanks, Neutron Andre. I'm in class. Can I give you a call after my class? Can I give you a call after my class? Can I give you a call after my class when I'm done with my class? The what?
Mm.
You need the process. The, the persons of stick, stuck, stuck, stuck. If you like stick glue, if you stick chewing gum on something, right? Pardon? Speak. Okay, now obviously you can say somebody spoke. Yes. You can say somebody spoke. Yeah. Okay. Please come again. KEEP. Yeah. Then it's capped, capped, capped. Yes. Yeah. Is it possible I give you a call after my class? Make. Like MAKE. It's made. That is the past. Made. Yeah. Yeah. All right. Thanks. Okay. Yeah. My apologies. Somebody just hijacked me now and was asking me about some other things. Okay. Next question, please. All right. Now we're looking at the range basis. It's a simple thing.
Mm.
Now, this particular map is a linear map defined like this. What is the basis for the range? All right. So the range would be, you break it down. How do you break it down? You break it down to the x's and so on. So you'd have the x, 2x, 2x. Okay, x to x to x. Right. And then now you have minus y. You have 3y. Okay. Yeah, minus y, 3y, and then there's no y. Right. We have x, which is 1, 2, 2. y, which is minus 1, 3, 0.
Mm.
Okay, so you have this. Right. Obviously, you understand that these things are from R2 to R3, so which means X and Y themselves are real. Okay. Right, so the basis for the range would have to be that. So the basis, you put this one. So it's going to be 1, 2, 2, and it's going to be minus 1, 3, 0. Okay, just picking these vectors there. Which one is that? It appears that is none of those. So the correct answer is none of those. Right, so we continue and we look at more problems and we solve more questions like the next one. Right, so the next one is about what we looked at now, something interesting, but easier of the exam type. Okay, suppose T from this is defined by this. Then the eigenvalues of T, oh yes, the eigenvalues of T are, okay, so obviously they put easier anyway. Right, so you need to choose. Let's just do the eigenvalues here. Okay, the eigenvalues is like we did before. So you have T of these, which is lambda that. Okay, so what is T now? We always write this formula, and then the map is defined like this. It takes xy to y and for x.
Mm.
So you have this. So which means that now this is going to become lambda x, lambda y. Multiply through by the lambda like we did before. And then now we compare the components. Y becomes lambda x, and 4x becomes lambda y. Okay, we need to solve this one simultaneous. Just like simultaneous equations. This.
Right.
Now, if these are simultaneous equations, we need to solve them in a clever way. Like this one is telling us that y is equal to lambda x. We must use it first. The one that makes either x or y the subject is the one we use first. So we're going to have this one because y is already the subject. The problem here would have to divide. So you can divide anyway, but this one is already having like a variable as the subject. So if you have this one, so you're going to say you put equation 1 into 2. Okay, if you put equation 1 into 2, all right, so you'd have therefore that lambda, why is this? So which means 4x is lambda. What is y? Y is lambda x. So which means 4x is equal to lambda squared x. Okay, like we did before, you can factor out and write this one as 4 minus lambda squared, which means x is 0 or lambda squared is 4. So lambda is plus or minus 2. Okay, obviously, we're interested in the eigenvalues. Eigenvalues are lambda minus 2, lambda 2. So which one of the answers is the correct one? It is none of those answers. Okay, so
Yes.
You have that? Okay, but this kind of question, please, you need to expect this kind of a question where you need to be able to calculate the eigenvalues and the eigenvectors.
All right.
In which case, it's extremely important to be able to calculate these.
Mm.
It's examinable. So here they ask us to find the eigenvalues. They ask also for the eigenvectors. So you need to be very, very ready to do those kinds of things. Next question. Okay, which of the following defines an inner product? Right, so obviously you need to look very carefully and think of which one defines an inner product. Right.
So I have a problem with this topic. What is inner product?
All right, yeah, good. So an inner product is like, what is a vector space? Okay, I'm going to define it now. When it comes to an inner product, we learn the axioms, like the axioms of a vector space. So I'm going to state the axioms of an inner product space because an inner product space has its own axioms, like the 10 axioms of vector space, but for the inner product space, normally there are fewer properties. So they're like normally 4 of the properties. But in which case, um, so
Let's continue, sir.
yeah, we're continuing now, but I'm gonna state the properties of an inner product space in terms of what an inner product space is. So an inner product space has the following properties. The properties. Let me write them here. Property number 1. We say that for each fixed vector, for each fixed vector u in the vector space, the function that takes v to vu is a linear map from v to f2. I'm going to be really fast on this one. 0u, the inner product of 0 and u is 0 for all vectors u in v. Property 3, inner product of u 0 is 0 for all u in v. Property 4, u together with v and w is the same as uv plus uw. Then we have the u, v, w, which are in v. Okay, property 5. Okay, these are the basic properties you need to know, and then we're going to use them to answer this question. These are like the laws. Okay, property 5 says what? U lambda v is lambda bar uv. This is for all lambda element of f uv element of v. Um, So which of the following defines an inner product?
Yes.
Okay, so you need to look and think, and here's the answer to that one. Right, so obviously looking at these very carefully, okay, this one is like each one is a function. So we must go through all this. Right, and we're going to look at the fact that, well, I mean, a very clear analysis reveals, therefore, that it's none of the above. There are a couple of reasons now here. Right. For example, if you look at UV, okay, I want to mention that we say ideally UV is VU.
Mm.
U plus V. W must be equal to UW plus. That's another way of stating this. So yeah, it's very important. So you have this here. What is it? VW 3. You have K UV. It must be equal to K. Okay, these are equivalent to what, but maybe they are more nicer, much more easy to apply. Property 4 would be the inner product of V and V is greater or equal to 0. Okay, so if you take the inner product of a vector with itself is greater or equal to 0, and VV is equal to 0 if and only if V is 0. Right. So yeah, you have this. I'm going to mention in passing that based on these things here and the observations, Roman figure 3, this one. So Roman figure 3 does not satisfy okay, Roman figure 3 does not satisfy something. I'm going to state that one. Okay, Roman figure 3 does not satisfy Roman figure 3 does not satisfy VV equals 0. If and only if V equals 0. Roman figure 3 does not satisfy VV equals 0 if and only if V equals 0. Why would we say that? We would actually say that because if you look at the inner product, 0 plus 0x plus 2x squared inner product, 0 plus 0x plus 3x squared. Okay, we have this inner product. But what is this inner product here? Right, so this inner product here can be clearly seen maybe you can do component-wise multiplication to find this inner product.
Right.
Right, so if you multiply 0 times 0, you multiply 0 times 0, you multiply 2 times 3, you get a 6. Right, so if you multiply them, and you get, what do we get at this point? Obviously, depending on the case, so if you're dealing with R2, all right, so what was these things? Okay, now, obviously, because these things are in R, okay, if you look at this one here, right, and now the result, according to this, what is it? It becomes A1, it becomes A1, A2, so we multiply this with this. So here, let's check this one. So it's going to be this one, 0 times 0. And next is going to be C1, C2. Right, it's going to be C1, C2, with C1, C2 is that. So which is going to be 2 times 3, which is 6. Okay. If you look at the result in that manner.
Mhm.
So now if you look at that, the choice of vectors, and what does this condition, the third condition, mean? Well, it means that this is 0 if and only if these vectors are 0. So my point anyway with this example is we're trying to get to a point where we have vectors whose inner product according to this rule is going to become 0. Like if you look at the 0, 0, 2, okay, 0, 0, 2. And then now what other vector would you have, for argument's sake, at this point? But you could have, let me come up with some vectors here. Okay, so let me do it in red. I'm going to be really fast in giving the example just to show that obviously it's a problem in satisfying this one. Right, so you would have a vector like -2, -2 plus 0x plus 2x squared, 3 plus 0x, and then minus 3x squared. For argument's sake, okay, let's consider these here. According to these, what would this be? Okay, it says multiply the first, the scalars. It says multiply A1, A2. So you're going to multiply this with that. So that's going to be -2 together with 3. And then you multiply C1, C2. You multiply the quadratic coefficients. Okay, the coefficients of the quadratic terms. So you multiply 2 with -3 for argument's sake. Okay, so this is going to be, allow me to make this one a plus. It's okay. So that here, this one is going to be a plus. So that this is going to be -6 plus 6. What is -6 plus 6? 0.
Yeah.
Okay, obviously, we've been able to just come up with examples here to show that Roman figure 3 does not satisfy that. This is 0, yet it does not imply that any of these vectors is 0, because -2 plus the 0x. So you can come in right here. So -2 plus the 0x plus 2x squared is not the same as the 3 plus 0x plus 3x squared. They're actually not the same. Not only that they're not the same, these vectors, but need to say more. because this condition says that this inner product is 0 if and only if the vectors themselves are 0. But obviously you agree that this vector 3 plus 0x plus 3x squared is not 0 plus 0x plus 0x squared. It's not a vector that consists entirely of zeros. So obviously in view of that, it's none of the given answers. But obviously under ideal conditions, one will have to test all these from 1 to 4. And I'm sure that obviously, but obviously these are multiple choices, so you can always look at an easier way to sort of arrive at the answers to these. Okay, so the answer to these would be none of the given answers. But these are the properties to be tested. It should be interesting to go through some of these. But once again, these are multiple choice. You don't need to show all the steps. Yeah, but yeah, in the exams, maybe one question can come out of these. Yeah, long one, proof, etc. Next. Okay, at this point, this one is a very interesting one. We need to find a matrix P that diagonalizes this. How do you find a matrix P that diagonalizes this? Right, so let's find these together in practice. First things first, we need to be able to find the eigenvalues. How do we find the eigenvalues and how do we find the eigenvectors? Right, and okay, eigenvalues. Right, so how do we find the eigenvalues? Well, there are many ways to find the eigenvalues. So to find the eigenvalues, you can consider the matrix A minus lambda I. In this case, I3. So that would be A, which is minus 3, 0, 0, 0, 1, 1, 0, minus 1, minus 1. And then you put lambda 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, and then what does this give us? Okay, so you just subtract along the main diagonal. So it has minus 3 minus lambda. Then you have 1 minus lambda, and then you have minus 1 minus lambda. So you have this. Right. So um all right. So once you get to this point, what do we do? We need to find the determinant of this, of A minus lambda I3. Right. Okay, what is the determinant of this? Well, the determinant of this is going to be minus 3 minus lambda. Okay, so you just expand along the first row. If you block this column in that row, so you have this. Okay, you find this determinant, and then you equate this determinant to what? To 0. And now, if this is the case, what do we get next? Right, so this would mean, therefore, that...
Yeah, sorry, say I had some load shedding there.
Please come again. Please come again. You have load shedding now. All right, I need to confirm if you have load shedding now. All right, you have load shedding now, I think. Okay, so which means that you have minus 3 which equals 0, 1 minus lambda equals 0, minus 1 minus lambda equals 0. We continue.
Yes, there's load shedding.
All right, there's load shedding. All right.
Yes.
I'll just finish this off.
It's can continue.
Okay, right. So lambda, at this point, what is lambda? So lambda is equal to minus 3. You can move this one across. And then here, lambda is 1. And here, lambda is minus 1. So we continue. So, right. So, right. So if you look at these carefully, right, what do we then get? So we need to then get the eigenvectors out of these. Right. Okay, so eigenvalues are lambda equals minus 3, lambda 1, lambda equals minus 1. So for lambda, for what do we get at the end of these? Okay, so we'll take these vector. You have to consider, I'm going to write this one here, which is minus 3 minus lambda 0, 0, which is 0, 1 minus lambda 0, which is 0, 0, minus 1 minus lambda, x, y, z. So if you have these, then if you put minus 3 here, it's going to become like 0. Okay, if you put minus 3 here, it's going to become, let me just show it an obvious step. So that's minus this, 0, 0, and this is 1 minus into minus 3, 0, 0, 0, minus 1 minus 3. So what are we getting then? Okay, this is minus 3 plus 0, 0, 0, 0, 4, 0, 0, 0, 2, x, y, z. 0, 0, 0. Right. So now what do we then get at this point? Right, so um ordinarily we need to row reduce this. Is it row reduced? So you have this. So so Okay, so you can say x here is x,
Mm.
which means x, y, z, which is x. So you have this. So the eigenvector for lambda equals 3 minus 3. The eigenvector is 1, 0, 0. Okay, we need to do one more. Hey,
Mm.
two more vectors. Okay,
Yes.
so yeah, let's just do two more vectors. For the other one, like lambda equals 1. Okay, I'm gonna be straight to the point here. Okay, if you have 1, you put it here. What does it give? It gives minus 4, 0,
Zero.
0. It gives 0, 0, 0. It gives 0, 0, minus 2. And then it gives x, y, z. And then it gives 0, 0, 0. Right, so it is clear that the minus 4, 0, 0, 0, 0, 0, 0, 0, minus 2, 0. This would be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, which is minus 1/4 row 1, minus 1/2 row 2, 3. Okay, the conclusion therefore at this point is that x is 0, z is 0, y is y. So x is 0, y is y, and z is 0.
Mm.
Pull out this one, which is 0, 1, 0. Okay, now we continue. We continue. Right.
Lambda.
Right. Okay, let me close a little bit here. So we got an eigenvector. Okay, this one, the eigenvector. Okay, I'm going to squeeze the other one here for lambda equals minus 1. Going to be very brief. So I was trying to elaborate. Right, so like here, if you put minus 1,
Mm.
which is minus 2, 0, 0. If you put minus 1, it's going to be 0, 2, 0.
Mm.
0, 0, 0. X, Y, Z. 0, 0, 0. Okay, this point, this would mean that X is 0, Y is 0, Z becomes Z because the row is entirely consisting of zeros, which means that if you have the X, Y, Z, you forgive me, I'm trying to squeeze this here. X is 0, Y is 0, and Z is Z. So it gives, so the matrix P that is required, okay, then you can compute that. Okay, I'm going to come back and compute it here. Okay, we're looking for the matrix P. Okay, so the matrix P is going to be consisting of the vectors. Like for lambda equals 3, is the vector is, the eigenvector is this one. For lambda equals 1, yeah, we did it here. For lambda equals 1, we did it here.
Mm.
0, 1, 0. And then for the last one, it became 0, 0, 1. Okay. Ordinarily, these vectors need to be normalized, but these vectors are of unit length. These are unit vectors. Who is this? Right. If this is P, these vectors are, so they are of these are unit vectors of length 1, and therefore they are normalized. Ordinarily, would have to normalize them because this one is a symmetric matrix. Okay. Now you take this matrix P, bring it here. So you would have, okay, I underestimated the amount of work for this one. But now you then have, for instance, this calculation. P inverse AP. So you have this one. What is P inverse? Okay, okay. And then we, yeah. Okay, but P inverse, this is like the identity matrix. So the inverse is the identity. Okay, we can find the inverse, but for the identity matrix, the inverse is itself. So for the identity matrix, the inverse is gonna be like this. Doesn't change. Minus 3, 0, 0. P becomes the same thing. 0, 1, 0, 0, 0, 1. Right, so now, what is the answer to this? The answer to this would be that P inverse AP. Okay, this is the identity times this times the identity. So the answer is the original matrix. It is the original matrix. So it is exactly that one there. It is exactly the matrix A. In this case, okay, for this problem. So these identity matrices will, if you multiply any matrix by the identity matrix, it remains the same. So it becomes minus 3, 0, 0, 0, 1, 1, 0 that. Right, so we get the answer. So now at this point, if this is the case, that becomes the answer. Please look at that and note it. Right, it is actually the matrix A that has been sort of obtained here. And if this is the case, the matrix A that has been obtained, right, we get, okay, I think there is a small typo error here. There is a small typo error. There's a small error in the calculation. You need to check it. Need to check it carefully. I think there's an error in the. Okay, let's check this one. -3. Just a minute. I need to check. -3 that and 0, 1, 1 and 0 that. Okay, and then now you minus this. Okay. Um. Okay, there must be lambda equal to 0 as one of the vectors here, as one of the eigenvalues. Right, so let me check again. So you minus this. So which is minus that? 0, 0. 0, which is minus that. Ah, okay, I missed a 1 here. Because this is 1 minus 0. So I missed the 1 here. And this one here is fine. It's just that I missed this one here. Okay, because I could see that it's a bit strange that we're getting the identity there. Okay, I'll just do it really quickly. So now, because of that, please allow me to quickly um, make the necessary changes here so that you can get the correct results to this question. Because now I have a couple of ways to always check my working. All right, so yeah, but that is the method. But obviously, we expect that find a matrix field diagonalizes this. We expect the answer to be a diagonal matrix, and now it's not diagonal, and that is why this made me think twice. So, and I could see that I missed just the one there. Okay, if you miss the one here, then if you find the thing, okay, so that's going to be minus 3 minus lambda. You block this and that. So it's minus 3 minus lambda, and then you'd have 1 minus lambda 1, 0, minus 1 minus lambda. So which is minus 3 minus lambda. So which means you multiply this and that. 1 minus lambda minus 1 minus lambda. So which means that what would the answers be out of these? Lambda equals 1. Lambda equals what? Uh-huh. Let's see. Okay, 3 minus 3, 0, 0, 1, 1 minus that. And then here you subtract this. And then, okay, I'd lost you. I'd lost you. Okay, I'm just cross-checking these results here to make sure we have the correct one. So you have this, you have minus this, you have minus that. So which is this? Uh-huh. I also missed the 0 here. I also missed the minus 1 here. Right. I also missed the minus 1 here. Right. I also missed the minus 1 here. And therefore minus 1 there. So you have this one plus 1. Now it's fine. So you have minus 3 minus lambda. And then you have this one, which is minus 1, minus 1, minus lambda, minus 1, minus lambda plus lambda, minus 1, minus lambda plus lambda plus lambda squared plus 1. So which is lambda squared. Now this one cancels out, and then we have minus 1 canceling out, and then we have just lambda squared like this. Yeah, this is super fine. This is super fine. So you'd have therefore that, yeah. So if you equate these to 0, you'd have that lambda is 0 or lambda is minus 3. So I'm going to make quick changes to this. Right, because you could see that the matrix could not just be diagonalized, so right, could not be immediately diagonalized. So yeah. Okay, so there were just ones that were missing, that were accidentally omitted, and now they made the matrix not to, because a diagonal matrix must have the one, it must have entries only in the main diagonal, and this one did not. So yeah, you have that. Okay, I'm just quickly trying to get this erased here. All right, we're done. But yeah, I realized there was some missing ones. The answer must be diagonal, please. Okay, there's a question like that in the exam, so this question is very important that you understand. But this matrix is symmetric, so if a matrix is symmetric, then um you need to normalize the matrix, the vectors. You need to normalize the vectors if the matrix is what is um the thing. If the matrix is a symmetric matrix, okay, this one is symmetric. Right, so we're right back now, and we here. So I would say for lambda equals 0, you would use this matrix here. Okay, so these are the correct eigenvalues. We're just missing one there. Okay, I just omitted the ones accidentally. So you'd realize, therefore, that okay, this matrix is defective. It's a defective matrix because if you put, okay, I can copy this matrix here, so it's minus 3 minus lambda. Minus 3 minus lambda, then you have 0, 0. And then you have 0, 1 minus lambda, 1. And then 0, minus 1, minus 1 minus lambda. Okay, then you have x, y, z. So when x is 0, so you have minus 3, 0, 0. 0, 1, minus 1. So this one is x, y, z. So, okay. Now this matrix is 3, 0, 0, 0, 1, 1, 0, minus 1, minus 1. Okay, we need to row reduce this matrix here. 0, 0, 0. Okay, to row reduce matrix, we need a 1 here. Minus 1/3 row 1, 1, 0, 0, 0. And row 3 plus row 2, 0, 0, 0, 0, 0, 1, 1, 0. Which means x1 is 0. Okay, I called it xyz. Okay, yeah, you can call it xyz. It's okay. So that the columns consist of x, y, and z. So you can call these, you can call them like that. So this is like x1, and this one is so okay, no. X is 0, but y is what? So y is not this. Y is minus z, because this means y plus z is 0. So y is minus z, and z equals z. I keep losing you. Is it a load shedding? I keep losing you. I think it's the network. I think it's the load shedding that I'm losing you. I think it's the load shedding, Mahauta. So you have this. Okay. Yes, this is the correct eigenvector. So for lambda equals 0, Okay, for lambda equals 0, the eigenvector is 0, minus 1, 1. So this one has algebraic multiplicity equals 2 because it's lambda squared. So in the true sense, lambda equals 0 twice because it's lambda squared equals 0. So okay, this one is of algebraic multiplicity 2 because it is lambda squared into minus 3 minus lambda, which means lambda equals 0, lambda equals 0, lambda equals minus 3. Okay, we continue, Mahauta. We continue. I know I lost you. Okay, yeah. So this one is of algebraic multiplicity 2, but this one is of geometric because it's a vector. It is geometry associated with it. The vectors have magnitude and direction. So it has geometric multiplicity equal to 1. In mathematics, so the matrix is not diagonalizable. And hence, there is no such P. P does not exist. Since this geometric multiplicity is not equal to you see, it's one vector to lambda squared to two values of the two eigenvalues that have the value 0. 0 twice because it's lambda squared. Geometric multiplicity 2, algebraic multiplicity 1, there is no such P. P does not exist. Now, also compute this. So the answer here should be that P does not exist. Let's remove this. So P doesn't at all what? P does not exist. Okay, so P does not exist. P does not what? Exist. So yeah. I can just appear and do more problems. So because you see, we're supposed to find the matrix P, so it's not there. Because this matrix must have, the matrix P must have 3 columns. But already we have a situation where this vector is only one vector. So, okay, this question normally has a bit more work. So it takes some good amount of time quite to calculate the vectors. But I'm sure the method is pretty clear. Okay, this is the method. But once you see that a lambda squared, which is 2 values of lambda that are the same, produces a vector that's only 1. It's defective because for us to get the matrix P, we must have 3 columns. But now the lambda equals 0 is supposed to produce 2 vectors. They produce only 1. So there's no such P. So there's no need to proceed. The P does not exist. So we can't be able to compute this diagonal matrix. So Find a matrix P that diagonalizes. So this matrix cannot be diagonalized. It's not diagonalizable, this matrix. So in other words, the conclusion here, matrix A is not diagonalizable. It's not diagonalizable. And then we're done in the thing, okay?
Yes.
Yeah, so yeah, we can have a discussion. Okay. All right, now, because obviously we have discussed and now we are well. Now the other things I planned, I know that the other things I planned, like your subspace questions, right? I spend a lot on the subspace questions because tomorrow there has to be a question that is gonna have this in a direct sum, like this one that says, suppose U is this, find a subspace WFF4 that is this way, and then another U, another one. This one is three of them. And then I wanted to also bring to your attention some other examples that are examinable. So you continue.
Yes.
Right. Right. So I think that because you see the time now is what? Okay. I know I wish you continue. But the time is 1838. And I know we started at 16 hours. In about 1601, we were on air. Okay. I think I'm gonna return. When will your power come back? At 8.
Yes.
Right. I think I can
8.
just come back and do 1 hour and do one more hour. To speak of
Okay.
more things that are gonna appear, like this.
All right.
Yeah, I'm gonna appear because yeah, okay. I'm gonna appear after. Okay, I'm gonna send the time so that I'm gonna appear when your power is back, and I can do these kinds of things. I was going to these direct sums and so on.
Okay.
So that we can be like good tomorrow. Also going to speak about these kinds of subspaces. This is subspaces that, like this one, I'll just mention it in passing. The set of all differentiable real valued functions on R is a subspace of R to the R. The set
Mm.
of all continuous real valued functions on the interval 0, 1 is a subspace of this. Okay, so I'm going to speak about these kinds of things. The set of all differentiable real valued functions f on 0, 3 such that the first derivative is subspace of. I'm going to discuss this in detail. Obviously, these relate to the function spaces because I'm going to first define as function space, then discuss these examples because this one came in the one of the questions where we said, when will this be a subspace? Is a subspace of F4 if and only if this number is 0, the B is 0. Okay, so
Yes.
obviously it's x3, 5x4, where the x3 and the x4 are coordinates. But the B itself now it's must be 0 for this set to be subspace. So I'm going to return again later, I think. Because we don't have time. I was going to say I'm going to return tomorrow, but I think that obviously it's the last day. Yeah, it's the last day today.
Yes.
So yeah, I'm going to send you the time. Yeah, because your load shedding happened. Now your power is gonna be back at 8. My load shedding is gonna be happening at 8. And now when it happens at 8, my network is not gonna be good from that time. So if my network is not gonna be good from that time, from
Okay.
8, so I'm not gonna be having power from 8 until 10. So which means that my power is gonna come
Okay.
back at 10. When my power comes back at 10, it means I
All
can
right.
return after 10. Think about this and let me know if that is
Okay.
ideal for you.
Yes, it will
As I
be
said, my plan is to speak of these kinds of questions where you need to deal with the direct sums. I just gathered them here. There are a lot of them. Like these kinds of questions. Find subspaces. We spoke about subspaces, but having to find specific subspaces that will make this a direct sum. Those are the kinds of questions I would like us to
mm,
obviously like discuss. And I brought a lot of them like this. I can return after 10. So you need to let me know if, because my power is going to leave at 8 and come back at 10.
mm,
Right. So let me know if that you have the energy to have a discussion as late as
yes,
11. Um,
yes.
yeah, I'm going to send you the time, but let me see. As late as 11, because, yeah, as late as 11 at night, because my power is going to come back at 10. Or as late as 11 at night, so maybe I can say it about 11:30, because when the power comes back, I'll have to catch up on things I would have missed. So I can only return, I think, on air at about like half 11.
Okay.
Yeah. So you think about it, and then yeah, half 11 is what I'm suggesting. I can return and just continue to conclude the things I wanted to speak about. Okay.
All
I'm gonna
right.
make this video
So,
available so that yeah, I'm gonna make this video available for you to watch. I'm gonna send it on WhatsApp in the next couple of minutes. Okay.
okay.
Yeah.
So what about linear transformation? It won't.
Yes, the linear linear transformations are they not gonna be there? They're gonna be there because
Oh,
the linear transformations like here, but yeah, there are certain things about linear transformations that I'm gonna speak about. Like this
okay.
is a linear transformation T, T from
Oh,
R2
okay.
to R3, it's a linear
Linear difference.
transformation.
All right.
Um, so linear transformation relates to eigenvalues and eigenvectors, but they can ask
Mm,
you to prove it is linear. So it's something that, like here, I said T is linear. Okay, I
mm,
said like here T is linear because linearity means that it must satisfy these two conditions. Obviously at this point, so I decided to just state this condition and just state that always the constants must be 0 for it to be linear.
yes.
When I return at half 11, I'm gonna speak of specific instances where a detailed proof on the problem that these constants like b and 2a and b bring when it comes to linearity. Okay,
All right.
yeah. So I'm gonna return at half 11 because of my power is gonna be right back. I would have caught up because I'm gonna lose power as well from 8 until 10. So at half 11, I'm gonna return same link. The link Zoom link is the same. If you are okay,
Mm,
so if you have the energy, you let me know. Then we can just continue and have some of the things that are important just for awareness purposes, and then we'll see what to
mm,
do. Okay,
and all
right.
right,
For
sir.
now, thanks a lot for joining us. I'll make the video available on WhatsApp just for you to play around with the video and see what you can do with it. Okay, but for now, thanks a lot, Mahauta. See you later. Okay, and goodbye.
All right. See you. Bye.
Okay, goodbye.
Bye.
Goodbye, Makauta.